All right, so today we're going to talk about something that's, well, it's a pretty radical new kind of computing. We're not just talking about software that pretends to be intelligent. Nope. We're talking about building intelligence right into the hardware itself. We're talking about building a brain on a chip. Let's just dive right in.
So I want to start with a question for you. Why is your brain more powerful than a supercomputer? Now that might sound like a trick question, right? I mean, surely a massive supercomputer built for insane calculations can outmuscle our humble human brain. Well, in some ways, yeah, sure. But in the way that really matters, not even close.
And this is where it gets crazy. A top-of-the-line supercomputer can guzzle megawatts of power. That's enough to run a small town. And your brain? It just sips on about 20 watts. Yeah, that's less power than a dim light bulb. So the real question is, how on earth is the brain so ridiculously efficient? And, can we copy it?
To figure that out, we first have to look at a fundamental flaw, a deep-seated problem in every single traditional computer out there, from the phone in your pocket to the biggest data centers.
It's called the von Neumann bottleneck. Think of it like this. Your computer's processor, the CPU, is kind of like a chef in a kitchen. The memory, or RAM, that's the pantry down the hall. Every single time the chef needs an ingredient, they have to stop what they're doing, walk all the way to the pantry, grab one thing, and walk all the way back. This constant back and forth, that is the bottleneck.
So, and this is the crucial point, most of the energy your computer burns isn't even for thinking. It's just for moving data around. It's an architecture that's basically built on inefficiency. And scientists realized that to even get close to the brain, they had to throw that whole design out the window.
Okay, so if the old blueprint is flawed, where do we find a new one? Well, we look at the one that's been perfected over millions of years of evolution, the physical structure of the brain itself.
This leads us to the core idea of in-memory computing. What if the chef could just cook right inside the pantry? In these new brain-like chips, the very same components that store the information are the ones that process it. There's no travel needed, and that means a huge leap in both speed and efficiency.
And what's so cool here is how it completely changes the picture. Instead of one big central processor that everything has to get funneled through, a neuromorphic chip is this big decentralized network. It's got thousands of tiny local processor and memory units all working together. It's parallel, just like our brains, where different parts are handling different tasks all at once. But getting the structure right, that's only half the battle. To really unlock that incredible brain-like efficiency, you also have to change the way information is communicated. See, computers speak in a constant, noisy stream of ones and zeros, but the brain, it speaks a much smarter, way more efficient language.
The language of the brain is the spike. A neuron doesn't just sit there being on or off. No, it listens. It waits quietly. And only when the input it receives crosses a certain critical threshold does it fire off a single brief pulse of energy. It only speaks when it has something really important to say.
And engineers mimic this with a really clever circuit they call leaky integrate and fire. Basically, a capacitor acts like the neuron, and it slowly builds up charge from incoming signals. But, and this is key, it also leaks a little bit of charge over time. This lets it forget old irrelevant inputs. Now, if enough signals arrive close together, boom! It hits the threshold and fires a spike to the next layer.
This whole fire only when necessary approach has a name. It's called event-driven processing. The system only wakes up and uses energy in response to an event, some new piece of information. The rest of the time, it's silent. It's just waiting.
And this is the real payoff. Unlike your computer's CPU, which is always humming along, always consuming power, a neuromorphic chip is incredibly frugal. And this matters a ton for things like remote sensors or medical implants. Devices that need to run for years on a tiny battery, only waking up when they detect something important.
So we've got the efficient structure, we've got the efficient language. But how does this thing actually learn? This is where it gets truly mind-bending. We're talking about a chip that doesn't just compute, it physically changes itself based on its experiences.
The answer is something called synaptic plasticity. In your brain, learning isn't just software. When you learn something new, the actual physical connections between your neurons change. Connections that get used together become stronger, and ones that are ignored get weaker. This is the hardware of your memory.
So how in the world do you copy that in silicon? Well, it all comes down to timing. There's this rule called spike timing dependent plasticity, or STDP. And it's simple. If an artificial neuron A fires just a millisecond before neuron B fires, the connection between them physically gets a little bit stronger. The chip literally learns that A is associated with B.
Let's just pause on this for a sec, because this is a profound shift. With traditional AI, you train a model, then you install that software on fixed, unchanging hardware. With neuromorphic chips, the hardware is the model. Learning isn't a software update, it's a physical rewiring of the chip itself, happening in real time. So, where is all of this going? If the ultimate goal is to truly replicate the brain, well, the next frontier is to mimic it even more closely, right down to the very particles that carry information.
See, all of our electronics today run on the flow of these tiny little things called electrons. But the brain, it's a wet, chemical computer. It runs on the flow of much larger particles, ions, like sodium and potassium. And it turns out copying that has some massive advantages. New research into what are called ionic transistors, which use fluids or solids to move atoms around, could be a complete game changer. These things can hold their memory even when you turn the power off. They can be built at the true molecular scale of a real biological synapse, which means you can pack in even more computing power. And they operate at such low voltages, they could finally, truly match the brain's incredible efficiency.
So let's just bring it all together. This table really summarizes the 4 fundamental shifts we've been talking about. We're going from simple binary logic to spiking logic that encodes information in time. We're going from a sequential data flow fighting that bottleneck to massively parallel processing. We move from separate memory and processing to a co-located design that gets rid of data travel. And, maybe most importantly, we go from static hardware that just runs software to plastic hardware that physically learns and rewires itself.
And this is really the ultimate takeaway. For, 70 years, we've been building faster and faster calculating machines. Now we are finally beginning to build machines that are architecturally designed not just to calculate, but to perceive, to adapt, and to learn in the same physical way our own brains do.
Now, this journey is far from over, but the blueprint is clear, and it leaves us with a really fascinating question. How close are we, right now? Which of today's AI chips are already putting these incredible brain-like principles into practice? Well, that's probably a story for another time. Thanks for joining me.